Swayam Prabha. Digital India. Educated India.
So let me take some examples. Alright, you have seen enough theory, I guess. I think theory is relatively simple. I hope you understand that. Okay, so this is again something that I have sort of created, but not too far away from reality. Okay, so again a sort of concocted example, but not too far from reality. Okay, this is a relatively standard structure. Okay, typically you will see this kind of a structure in rotating systems again. So and this term would usually be here, yeah, but I have sort of switched it because otherwise it becomes a slightly tough example. Okay, we can look at the more tougher one also later, but for now let's look at this. Okay, aim is stabilization, which means that I want x omega to be L infinity and x omega to go to 0. Again we can also do tracking, but in steps later on, let's not worry about it. So now how do we start? You've seen what's the first requirement now? Okay, so let's try to identify what is psi, by the way, not zeta. That's okay, yeah. Here there is no psi, it's the omega state, right? We have the x and the omega state, the integrator, and also notice that I deliberately made it not look like an integrator. Huh? That was the purpose of making this example. Yeah, the second stage doesn't have to be a pure integrator. It is not. You see, it's not a pure integrator, which is, it's not a big deal, as you will see. Now tell me something. What do we say? We assume something nice for this system. What do we assume? We start with the first system, right? That's the whole idea. You start with the first system. What do we assume for the first system? Huh? Yes, but yeah, so existence of a k naught x and existence of a CLF, right? What is it for this system? Very simple, scalar. What is a CLF? What is the k naught x, you think? So step 1, guess V0x and k naught x, yeah, for this system, for the first subsystem. We always start with the first subsystem. That's how backstepping begins. What is V0x? What is k naught x? Anything. Give me some choices. Anything that comes to your mind. I mean, you've now seen enough Lyapunov candidates and Lyapunov functions and so on. Give me whatever, anything. Yes? No, just V0x. You always start with the first subsystem, forget the second. Huh? What is it? X square. Okay, thank you. My hearing is bad, sorry. So V0x equal to x square. I want to test this. Okay, alright. As a CLF. Let's see. How do we test if this is a CLF? Let's forget about doing K0x, but how do you test that this is a CLF? Do the usual tricks. What is it? V0 dot. It is what? Okay, I will take half x square. So I will get V0 dot as what? X omega. Huh? In this case, omega is the control. Huh? Okay. So omega is notionally the control, right? Because we don't have a second system in our mind as of now. Omega is notionally the control. Okay. So if we said that, so what do we need? If the control vector field goes to 0, and the drift vector field has to be negative for all non-zero x. But what is the control vector field? X. Sorry, not the control vector field, but the partial with respect to the control vector field. So LG V0 is actually x. So LG V0 is actually equal to x, and if this goes to 0 means x equal to 0. Okay, and so there is no other possibility. You don't have to check anything is negative or anything. It's trivially true. Okay, implies LF V0, no need to check. Yeah, it's trivially true. Okay, so such cases are a little bit weird to deal with, but they are okay. That's not a problem, because essentially you are saying x will be 0 if the control vector field is 0, and that is the equilibrium anyway. So you don't need to go anywhere else. So you are done. That's the logic. Okay, so done. Great. So this is a valid CLF. Valid CLF. What about K0x? How do I choose K0x? What is a good controller for x dot equal to omega system? Linear system, simple system, no? What is a good control? You can guess, or you can use the Lyapunov function you have to do Lyapunov reshaping. So fine, you already have V dot is x omega. What should I choose omega as? Minus x. Okay, I will choose minus kx, just, or minus, yeah, just to keep it a little bit more general. It will work for any positive k, right? So these two are done. Okay, because this will give me, implies V0 dot for this case will be minus kx squared, which is negative definite, which is the Wx we were talking about. Great, done. Step 1 accomplished. Step 2, go to the next system, right? Construct V x omega and find control. So folks, what is Vx omega now? V naught x plus what? Half norm of error between what? Omega minus k0x, which is omega plus kx squared. Yeah, it's a scalar, so norm is just a square. Okay, excellent. So I'm not going to use the formula that we, because backstepping is a procedure. Yeah, the purpose of showing you was the procedure, so we don't have to go back to those formula and remember and implement those formulae. This is easy. Okay, now what? I need to find the control. What will I do? Take the V dot, right? We've been doing this. Take V dot. Okay, and that's equal to V0 dot x, right, which is basically x omega now, plus omega plus kx omega dot plus kx dot, right, and this is x omega plus kx. What is omega dot? It's omega cross x plus the control plus k omega, and I have just substituted for the dynamics. Now what will I do? I use the same trick that I did before. This term here I write the omega as in terms of my new variable, that is this omega plus kx, right. So I can write this as minus kx squared plus x omega plus kx, right. So this term becomes these two terms. We did this even in the previous steps, right, and omega plus kx times omega cross x plus u plus k omega. Yeah. Now notice that I already get the nice term, right, the wx already showed up, right, it like it did in the general case also. This is the wx, this wx shows up immediately. Yeah, all I did was write this term in terms of the new variable, sort of the new variable that I have created, right. I want to write everything in terms of the new variables, which is x and omega plus kx that I have appearing, okay. That is what I did. I wrote this omega as omega plus kx minus kx, and that gives me this guy, alright. And now I know that this term can be combined with this term, okay, no need to take transpose either, it's too easy, right. So basically I have minus kx square plus omega plus kx u plus omega cross x plus k omega plus x, alright. Yeah, so I already know this is a CLF, not a problem. I mean, if you want you can work hard and you know that the term multiplying the control is the LG bar V, and if this is 0 means omega equal to minus kx, so this entire guy goes away, okay, and this is negative, okay. So all good, no problem, okay, alright. Now what would be the control now? If I wanted to use this Lyapunov reshaping idea, what would be a good controller here to make sure that V dot becomes negative definite? Just like we did for the general case, what would I do? Minus omega cross x minus k omega minus x, cancelled everything, and then minus omega plus kx, right, simple. Yeah, and you can run as many simulations as you like, this will always work. This is a very good controller, it will work beautifully, okay, even if you add disturbance. So all Lyapunov analysis, again we did not do this, but maybe I will do this maybe a little bit later because you have not done all the design, but any Lyapunov design or Lyapunov reshaping or any of the methods that we do, it gives you free robustness. Robustness is free. You know, somebody might tell you that, oh, but this is very theoretical design, and you know what will happen if there is noise, there is disturbance, which is true. How will your control? It will perform well. Okay, it will give you bounded nice performance because robustness is free in Lyapunov analysis. Okay, and we'll sort of try to understand. Basically, any CLF based design, by the way, not in general. There are, if you proved or if you use the LaSalle invariance type methods, which allow the use of semi-definite functions to prove convergence and stability and so on, they will not necessarily give you robustness, not guaranteed robustness. But anywhere where you use CLF based design, right, which is these, whatever we are doing a CLF based designs, will always give you robustness for free. Even if you add disturbance to your simulation, and we will give you assignments in this direction, okay, where you will add noise, you will add disturbance and so on, and you will see that your performance remains close to ideal. Okay, you are not going to deviate, it is not going to destabilize your system. Okay, so that is of course one of the features. In most cases it is also possible to compute how much the disturbance will impact your performance. Okay, it is possible to compute. Okay, again if I find some time we will cover this, how to compute. Yeah, it is also possible to control the effect of disturbance using control gains. Okay, for example, what is a control gain here? I will mark it. This is the control gain. Yeah, unlike your typical PID control, you don't have very, sort of very obvious PID type gains. Okay, here the gains are a little bit more complicated. So how you will look at this sort of a controller, in fact I would say, I would not call even this as a control gain, I will call this as the control gain. So let us see. These are the feed forward terms and these are the feedback terms. Okay, the logic is pretty straightforward. Okay, if you look at these terms, they are coming about just due to the dynamics of the system. Okay, these are just the dynamics terms coming from here, just the dynamics of the system coming from here. Okay, and you are sort of cancelling out the dynamics. Yeah, you are cancelling out the effect of the dynamics. Yeah, these are therefore called feed forward terms. Yeah, it means that you sort of predict what the effect of the dynamics is and you cancel it as best as you can. Obviously you can never do it well, therefore it is called feed forward term. The feedback terms like this term and this term and this term are actually the stabilizing terms, because this term is coming from here, yeah, and this term is coming from here. Okay, these are actually the stabilizing terms, both of these, not just one. So these are the feedback terms, they are actually the terms that are used to stabilize the system. I mean, it's a little bit complicated. I mean, you can also remove this, and because there is already a k here and all that, so it might seem like there is only one stabilizing term. This is not necessary to include. Yeah, in fact I could also not have included in the control law at all. Yeah, I can just adjust it in the k, as you can see. Yeah, so this term does not even need to be there in the control law, therefore let us not worry about this term. This is actually the feedback term. Yeah, and you can see again there is a lot of parallels here. It's a nonlinear system. Yeah, notice it's a nonlinear system, small nonlinearity, still a nonlinear system. Okay, but the control that you got is actually a PD control. Yeah, because this is a proportional and a derivative. Okay, this is a proportional term and this is a derivative term. So if I again want to label more, this is the D term, this is D term. So PD control. And so most aeromechanical systems, again PD control works very well. Usually the control for nonlinear aeromechanical systems will be PD plus feed forward. Okay, so this is what this is, right? It's a PD plus feed forward control. So applied controls folks or control engineers will typically use this terminology. Yeah, they'll have PD, feed forward, feedback and these kind of terms. But the feedback terms are essentially proportional derivative, right? Because you took x and omega, which is proportional derivative. Alright. A lot of people also wonder why a lot of PID works a lot of times, right? I mean, it's a big question, right? Why does it work all the time, and why do we do all this nonlinear design if PID works so well? Typically PID will work well when you don't know the feed forward terms very well. Okay, so what the I does is it sort of, at least in the linear domain, by the way, PID works only in the linear domain, actually it does not work in the nonlinear domain. If your oscillations are too big, then it will not work well for you. So what you try to do is you try to maintain the system in a very linear zone and then you apply the PID, works well. Okay, so in the linear domain these terms will have relatively smallish contributions. Okay, and so the integrator is what creates this internal model, right? So it adjusts the steady state error. Okay, so these terms, so the I is essentially replacement for these terms. Okay, when you don't know these terms too well, you would employ an I term. Okay, that's sort of the purpose of, or sort of the principle why PID will work relatively well. Yeah, it sort of I, if the integrator term is what, it's a 1 by s, right? So 1 by s is what, it's an integrator, right? And this system is an integrator, right? Just like most aeromechanical systems, I said, right? It has an integrator built in, right? So the I term is an internal model. Yeah, a very standard idea that if you have the internal model in the controller, internal model of the system in the controller, then you can kill the steady state error. Okay, you can also prove this. I think if you've done a good frequency domain course, there is proof of this also. Yeah, I don't remember it, but it's not difficult. Yeah, so if your controller has an internal model of the system, which is what? Which is saying I know the feed forward terms. What does it mean to have an internal model of the system? Means I know the feed forward terms. Right? So if you don't know the feed forward terms very well and you are working in a sort of linear domain, then 1 by s is a good internal model, and that is an integrator, and that's in your controller, works well. Yeah, cancels your dynamical the feed forward effects, and then you have a nice damping reaching. Yeah, proportional is reaching, dynamic D is damping. What gives you the sort of stops your system in some sense, doesn't have crazy oscillations. Okay, so that's the idea. All right, so you can say this is a way of designing CLFs so that you can come up with controllers. Typical controllers for aeromechanical, you will find them to be PD, feed forward structure. Okay,